Hey, this is Jordan. I'm going to be covering the very basics of VHDL, particularly going through this free range VHDL mini textbook that you can get for free, as well as just jumping into a bit of code. So, let's get started. Free range VHDL, you can just Google this and find it online. It is free, it is wonderful, it is short considering it's an instruction book, it's a mini textbook, but it's not bad to read whatsoever. And so this is what I'm just going to skim over what VHDL is. I'm assuming that anyone watching this has had some programming experience. I have a strong background in C and other C type languages. I've got some Python, a little bit of this and that. So I'll often be comparing VHDL to other languages. That's my basis. I hope everybody has a similar basis. Jumping straight in, there's a couple things to learn about VHDL. First thing is, and everyone who knows FPGAs will always tell you, VHDL is a hardware design language, it is not for software. And people keep saying this and it doesn't make much sense, but eventually you figure out why that's important. But it's there. When you actually start writing code, it's going to operate differently and it's going to be implemented differently than software would. For tools needed, I use Notepad++, just here on a Windows machine. We will talk about Model Sim later, and then you will also need something to compile everything and an FPGA to put your code on, to put your image on, my bad. And there's Xilinx, there's Microsemi, there's Altera, there's a couple of options there. So, jumping down further, this is just some of the quick and dirty sort of introduction to VHDL. I would highly recommend you reading this entire thing, but here are the high-level things to note. VHDL is not case sensitive. It's really nice if you can keep things in a nice order, but VHDL doesn't care. VHDL is not white space sensitive, unlike Python, if anyone's familiar with that. It's not that way. Comments in VHDL uses a double dash before things, such as right here. You can see this text is green because it's got the double dashes. It's a comment. It gets ignored by anything that actually runs the VHDL that you've written, whereas this is in black, doesn't get ignored. Parentheses are wonderful. I think they're great. Maybe that's just because I've got a big background in C. But in a lot of places in VHDL, parentheses tend to be optional. I think it makes code more readable, but you do whatever you want, as long as it works. Similar to other coding languages, we've got if, case, and loop statements. We'll go into those a bit more, and we'll see that implemented. If-else statements, this tripped me up for the longest time. If you say, if something, do this, else if, do this, else if, they take off the E. It's really weird, but it's what they do. It trips me up a bunch of times. And then we've got a list of reserve words, some of which I know, some of which I don't. They have some coding style suggestions for naming variables and keeping things nice and neat. I highly suggest finding something and sticking to it because it will help you. Jumping down into this third chapter. So, in VHDL, what you do is you define a piece of hardware. It will eventually be hardware. So, for starters, at the top of every VHDL file, you'll have an entity block. And all this entity block, it starts right there. Entity, you give it a name, is, port, and then you've got these parentheses, and the parentheses end there. And then you end my entity, so the entity ends. We do use semicolons at the end of a lot of lines, not all of them. This can also trip you up. Anyway, but an entity is pretty much your black box drawing. So if you're drawing on a whiteboard, these are all of your inputs and your outputs. So for this case, we've got this thing called killer circuit. And then we say we have an input of life in, it's an input, so life in, Life in 2 is also an input, and then control 1A, control 1B. And this is really nice to draw out physically. Whiteboards are great, pieces of paper are great, and then you've got your outputs, kill A, kill B, kill C. And so this defines what signals everything above it has to worry about. Everything else inside this black box, that's what all the rest of your code will be in a given file, but nothing else is going to care. All this does, this entity block, is it just outlines what every other block will have to care about, which is your inputs and your outputs. If we keep going a bit, again, highly suggest you reading all of this. Here's an example of an entire file, and again we've got this entity declaration right here where we declare A, B, and C are inputs and F is an output. And then this architecture part we'll get into a little bit later, but that defines what goes on inside of this block. So entity is what everything else outside sees, architecture is what actually happens on the inside. And I think that's it for this chapter. Keep cruising through. So this is, concurrent statements are really where VHDL is different from most software languages that you might have learned. Naturally, because all of this will be implemented in hardware, it does not have a processor to do a single command on a clock cycle, do another command on another clock cycle. Inherently, VHDL wants to set up circuitry, close quote, circuitry, I'm doing air quotes, inside of an FPGA, and all of that will happen simultaneously. So this is a concurrent statement. You've got your entity declared, so this is what everything else sees. Inside your architecture, this is what happens. However, this is what would normally get executed in a software language, but in VHDL, in an FPGA, it's not going to get executed like you would think. When it says begin, you wouldn't step through your code and first A out would get assigned, and then B out would get assigned, and then C out, and then E out. It's not how VHDL works. Because this is a concurrent statement, on every clock cycle, all 4 of these will happen at the same time. And so there's no this will happen first, this will happen second. Anytime you have a concurrent statement, which is the natural state of VHDL, everything happens simultaneously, which is very important to note because you don't want things happening out of order. Keep cruising down through here. There's a ton here. The assignment operator, so in languages like Python and C and other things, you just use an equals. You know, you've got a variable here that you want to assign a value to, and so you say B out is equal to this stuff, but here in VHDL, the assignment operator is this little arrow guy. So it's a bit different, takes a bit of getting used to, but that is what it is. I'm going to skip down here to a little later, a bit too far, 53. So even though I said that concurrent statements are what naturally VHDL does, you can do sequential statements like you would traditionally want to do in a software language. So when you do that, you notice we still have the begin like we saw before and the end for that begin, but then we define a process within the concurrent statement. So what this is saying is inside this begin, everything on this level, on this indentation level, is going to happen concurrently, but since there's only one thing, and because it's a process called proc1, then this will execute sequentially. So this is where if statements come into play, and this is where you can assign things, and if you were to step through, quote unquote, step through your code, it would first check this if statement, and if it was right, then it would go here. I mean, if it was true, else if, again, minus the E, which is weird. Anyway, and it just steps through this one clock at a time. So you can take advantage of both of these, and you will need to make effective designs. Too far. Wonderful. Finite state machines are amazing, and it's what I've used most of my VHDL knowledge for, but it is a whole nother topic unto itself, so we'll get into that in the next video, maybe the one after. But it's good stuff. The one thing I do want to mention here with finite state machines is one-hot encoding. Hopefully you've heard about it, but here in this figure you've got different states, and each of these states is represented by a number. So here it's 1 followed by 3 zeros. This state, it isn't like 1 1 followed by 2 zeros. It swaps out where the 1 is. This is called one-hot encoding. So we've got 4 digits, 4 states. This is a standard for a lot of things you will run into, and if you don't do one-hot encoding, you will often find issues that are kind of unexplainable until you fix it to be one-hot encoding, and then magically everything works like you think it should. It's important. You can go into the theory and you can look up one-hot encoding more, but just wanted to mention that it is important in VHDL. We are going to jump down to this last chapter. Signals, variables, and constants are mostly what you'll work with. You can think of a signal as like a global variable in C. You can use it whenever, and signals are what an entity is made up of. So signals can be passed in between different VHDL modules. Variables are private variables, they're local. So if you declare a variable inside of a VHDL module, a file, then unless you do something really cool and interesting, you can't access that variable, and you can't see it, and you can't put it as an output to anything else. So signals are mostly what you use, but variables can also be useful. Constants are constants, and they're great for what they do. There's more on assignments. Like I said, I would highly recommend reading all of this because the entire thing is good. It's 100 pages, but it's got some really good examples. It's got some problems at the end. Anyway, so that is some of the basics of the free-range VHDL book. Now I just want to pull up some VHDL code here that we are currently using and just show off what a file looks like, what you want to do. So because of the coding standard we decided to use here working on a project, there's a header of just information on what we're compiling this thing on, what FPGA we're using, and just good notes. It's good. Documentation is always good. It's a pain to do, but it's nice. These top couple of lines, IEEE is wonderful, and IEEE has set the standard for your data types. If you include the IEEE library and then these packages within the library, you get access to standard logic and standard logic vectors, which are your best friends, and that is what VHDL will primarily use. You'll use others occasionally, but it's almost always standard logic and standard logic vectors. You can think of standard logic as a bit, as a wire, and you can think of a vector as a bus, a group of wires. So here to start, we include the IEEE library and make sure that everything is nice and neat. Then we start the entity. This is a status timer, which ultimately will feed into the next VHDL file we'll look at. So we say entity status timer is. You'll notice Notepad++ does nice things. These words and letters in blue are reserved words, so use refers to a specific function. It makes it so it makes sure it uses this library. Anyway, so entity is a reserved word. You can't name like a variable or a signal entity. Anyway, so entity, our black box overview, we're calling this thing a status timer, and we're saying it has 1, 2, 3, 4 inputs and 1 output. These are the names for the inputs, and then, like I said, these are 1 bit, 1 bit, 1 bit, and then this logic vector is a bus. This, in this case, is 32 bits wide. So in languages like C, you've got the difference between ints, chars, longs, which automatically builds in how wide something is. But with a standard logic vector, you define how big it's going to be. It's nice to keep it at, you know, byte increments, but you can do whatever. So this count val is an input. It's a standard logic vector, 31 down to 0, so that's 32 bits wide, and then 31 down to 0. You could also do 0 up to 31, I think. Anyway, point of this is there's an endianness question, because endianness haunts everything you ever do. As long as you pick a standard and stick with it, like saying big number down to small number, you'll always be fine, as long as you're consistent with what you do. Anyway, so this entity, we've got clock in, we've got this colon that needs to be here to say this clock in signal is an input and it is a type standard logic, and then we've got our semicolon to end the line. You see that all the way down. This last line, these are always a pain, I always trip up on these. The last line in a port declaration, we've got done, the colon, out, standard logic. You notice there's not a semicolon here at the end, because that semicolon is after the end of the parenthesis. It's obnoxious because I feel like I miss it all the time, especially when starting up a new file and copy and paste errors. But things will yell at you if you don't do that right. So that's nice, but it's always a pain. So that ends our entity. That describes what this is going to look like to the outside world. Then we have our architecture. We call it architecture behave of status timer. So this black box that we made, this is how it's going to behave. We see the behave start and the end behave down here. After the architecture declaration, like I said, again, this is what this block will actually do, is inside this architecture. So after architecture, you have space where you can declare local variables, local signals, if you will. So in here, we've declared a signal counter. It's a standard logic vector, and it is 32 bits wide again. This is the assignment operator for a standard logic vector. It's a colon equals, and then this says that this value will be hex. You use double quotes for a standard logic vector, and then a semicolon at the end. So this just declares a signal and gives it a value, which I can't remember. Maybe I'll have to look through the free range VHDL, but this might just be a value for simulation. I'll have to look into that. Anyway, so architecture, we declared signals we'll be using, and then begin. So begin is what actually happens. So in here, we declare a process. Because this is a counter, we want it to make a couple of assumptions and to clock through to do something sequentially. So we've made a process called clock watch, and when you make a process, you have these parentheses right here, and this is called a sensitivity list. So anything in a process that you use to make decisions on, you put in your sensitivity list. And what I mean when I say make decisions on is, in this process, here's an if statement that uses the variable reset active low. And so because we need to know whether our reset is a 0 or a 1, we put it on the sensitivity list. If you don't put it on the sensitivity list, bad things happen, because then the process can't really see this signal and just bad things happen. So we've got our process, which is called clock watch. We've got our sensitivity list, which is everything we make a decision on within the process. We begin the process. So this begin is for the architecture, and it ends here this begin is for this specific process, and it ends here, hence end process. So once we jump in, we've got an if our reset active low is 0, then that's saying if something from the outside is telling us to reset, then we assign counter to be whatever's on the counter val. So this is very common for a process. For a VHDL module that you make, you want to stick in a reset, because you always want whatever you do to go into a known state if you have a reset. So first things first, if there's a reset, if it's equal to, in C you would do double equals, VHDL you do not do double equals. There's a lot of little minute details like this that are different, but you get the hang of it. If this reset is equal to 0, notice because this is just a standard logic, this is just a single bit, instead of using the double quotes like we used up here, we'll just use the single quotes. So if our reset is 0, then we set our counter to a known value, and we set an output to also a known value. So if we're in reset, great, we do that. Else if, so if we're not in a reset, on the rising edge of clock in, you always need to have a clock on all of your FPGA modules, because if you don't have a clock, nothing changes, the module doesn't know what to do. So clocks are very important, and you will learn this. So on the rising edge of a clock, which is kind of the standard, on the rising edge of a clock, do stuff, and in this case, if we're enabled as well, sticking enables onto modules is also very useful, because you can toggle things on and off from the outside. So this is fairly standard. If we're not in reset, and if there's a clock going and the enable says we should be going, then we take and we check if the counter is less than or equal to 0, then we say done, and we set done to be an active high signal, and then we reload the counter signal with the counter val. If not, then we take whatever was in counter and we subtract 1 and store it in counter, and we make sure the done is not asserted. Now, hopefully you've noticed that some of these things are zeros, some of these things are ones. You have to decide on your conventions for your active low or active high signals. What I've seen as a lot of people's standards is their reset lines will be active low. That's why this variable name has asynchronous reset underscore L. So that's saying that this is an active low, which means that when it is a 0, you should be in reset. Whereas most other signals, like the enable signal, is an active high. So that's saying that when reset is sitting at a 1, you're not in reset. When it hits a 0, when it's active low, you should be in reset. Enable, in this case, is an active high, so a 0 means you're not enabled, a 1 means you're enabled. This is all just stuff you have to figure out, and stuff you have to make a standard for yourself and stick with it. So pretty much what this whole thing does, in a nutshell, is you've got a counter which starts at some value, counter val, which is passed in, and then it counts down. When it hits 0, it says I'm done. And then when it's done, it'll reset counter to be counter val, and it'll put the done signal low again. So after 10 clock ticks, I guess this is F. So for our purposes, hexadecimal F is 16. So after 16 clock cycles, the done signal will toggle high for 1 clock and then go back down low. So this is a very basic VHDL file that works. Now I'm going to jump into one more slightly higher level VHDL file that will just explain some more concepts. This is a higher file that actually uses this lower file. So this status timer file is a simple counter. This system clock takes and uses that counter to make a counter that counts up and counts, in this case, the milliseconds of how fast things go. So again, we've got a bunch of comments up here at the top talking about what we do. We've got our library, make sure that it's IEEE. Again, as you can see between the two, they've used all caps for IEEE in this one, and this one is not all caps. Again, VHDL is not cap sensitive. So this entity is called a system clock, and again, entity, you just declare the top level, the inputs and the outputs. So port, we've got a clock going in, we've got a reset signal. This is not a active low reset signal, and then we've got a system clock value, which is out. Again, you can use tabs to line these things up nicely, so you can quickly see there's 2 ins, 1 out, standard logic, standard logic vector. A couple more tabs, and putting notes out here on the side is very, very helpful because you can lose track of what's what. So the system clock module will incorporate everything that was in this lower status timer, and we'll see that up here. So we declared the entity, we declared the top level inputs and outputs, and then the architecture, we declare a couple signals. So we've got a tick, a load, and a counter, and so these have the comments next to it. We can do some better alignment, make everything nice and pretty. Again, we've got our standard logic vectors, single quotes for a standard logic, double quotes for a standard logic vector. Hex is just for convenience. You can write it out in binary, but that gets a lot longer, and it's not as nice for a lot of things. Anyway, so this is what I was talking about. We declare, before we begin what we actually do, we declare a component in here. So this component declaration of the status timer is saying that this status timer VHDL file .vhd is going to be pulled in right here. And so we say component status timer, that matches up with what this is called, entity status timer. And then you say for this file everything that you're putting in and everything that you're taking out of this lower level file. So we've got a clock in, reset, enable, count val, done, and then similarly clock in, reset, enable, count val, done. It's just a repeat, copy and paste, so that this upper file can see everything, all the inputs and outputs of the lower file, and it can manipulate it. So we jump in here, we begin. So we've got a process down here, so this process will go sequentially. However, things like this will happen concurrently with this process. So every clock cycle, this load signal will be given this value every single time. And while this is constantly being assigned, this process will also go. So here we begin, we declare what this load is going to be every cycle so it doesn't change. And then we declare my counter of status timer. So this is saying from now on, this status timer, this lower level file, we are going to make our own, and from now on we are going to call it my counter. And we're going to say now that this status timer has this clock in signal that is its input and goes in right here. But for our purposes in this file, we're just going to call it clock. And this is convenient because our input to this file, we have a clock coming in, and here we're just saying that this clock is also going to be the clock that the status timer is running off of too. Again, same with the reset. It is an input to this higher level, which gets passed directly to this lower level. Here, we can turn on or off this status timer, this lower level file, But for our purposes, we're going to say, because it's an input, we have the arrow pointing this way. Our enable is always going to be 1. We're always going to be running this counter. And then down here at the end, counter val, we are constantly assigning it this load value so that we can load in whatever value we want, but we are constantly assigning it this value so it will never go above that every time it gets reset or stuff. And then this done signal we are routing out to this signal we declared called tick. Anyway, so you can also see, again, you got to keep track of all your semicolons. This port, semicolon, 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 no semicolon because it's here at the end of the parentheses, if I can click on it. And then similarly, when you do a port map, this is saying we already know we have these signals, let's map these signals, which again appear on this left side, to signals we have in this right side, which are what we're using up here. Anyway, and then we begin a process called clock watch. We only care about the tick and the reset. Again, the reset, this just sets our system clock value to be 0. But if we're not in reset, on the rising edge of tick, so this looks for the done signal, we've got our lower status timer, which every 20 clock cycles will toggle the status timer up and then down. So when we see that rise up, then if we're at a max level, we will roll over. If not, we increase our counter value. So hopefully this wasn't too confusing, but ultimately what this is, the system clock system is just a clock that counts up once every millisecond. And we can say that it's once every millisecond because we know the clock we're running off of is 20 megahertz, and so if we wait 20 clock cycles, that is 1 millisecond. So we have our counter, which is what this millisecond clock goes at. So every millisecond this counter value goes up by 1, and that goes up by 1 until it gets to the very top value it can be, which then it rolls over back to 0. And this counter value gets incremented every time our lower level counter, our status timer, gets through 20 clock ticks, and this one starts at 20 and it counts down to 0. There are various times where you want to count up and count down. This is very low level. There is no state machines involved in this, but hopefully this gives you a general idea of how to do things. This isn't too high of level, but it can be overwhelming. Anyway, the next thing we're going to jump into, and I'll wrap this video up and we'll start another one coming here in a bit, is the wonderful NAND Land, which is a great, again, free tool. It's got a lot of resources. Click on VHDL, and we'll jump into here. We'll talk about using model sim and actually seeing these things run. So, thanks so much for watching. Hope you learned something.